Section 10.4 is titled Nuclear Reactions, but I think it should be really titled Nuclear Decay or Nuclear Decay Reactions, because we're going to look at primarily three different modes that nuclei will decay into a more stable isotope, or at least a less energetic isotope. So looking at the history of nuclear radiation, we know in the early 20th century, late 19th century, we started to understand this natural radioactivity. The work of Becquerel and Curie certainly started the whole field of nuclear physics. And early 20th century, Ernest Rutherford analyzed some of the radiation emitted from samples of, for instance, radium. Radium was very important to his experiment with gold foil, where he was able to determine the very small size of the atomic nucleus and its high density. In any case, Rutherford found that he could identify two different types of radiation, the least penetrating of which was termed alpha. The more penetrating radiation was called beta. And then separately, Peter Villard discovered an even more penetrating radiation, which was called gamma. Initially, people didn't understand what these rays were composed of. And again, alpha particles are so poor at penetrating that they can't even really go through a couple layers of paper. Beta particles can penetrate a few millimeters of aluminum. These are normally the beta minus. We'll differentiate between beta minus and beta plus. And gamma rays, the most penetrating, can actually penetrate several centimeters of lead. So initially, these different types of rays, alpha rays, beta rays, and gamma rays, were classified according to their ability to penetrate different types of shielding. Later on, it was discovered that the alpha particles were actually helium nuclei. This was done in a very ingenious way. They took an alpha emitter up against a thin glass wall, which was evacuated, allowed the alpha particles to penetrate into the evacuated vial. And then they ran a current through it. And obviously, you run a current through a gas and you're going to get an emission spectrum. And they identified the emission spectrum as belonging to helium, and the alpha particles were then identified. The beta particles were identified due to their charge to mass ratio. Already, the electron had been characterized, and if you place a beta particle in a magnetic field, you will see that it follows a trajectory that we would expect for a negative. This is the Lorentz force, by the way, what we'd expect for a negative particle. When we look at, measure the velocity and, measure the centripetal force, we can determine that, again, the charge to mass ratio was that of the electron. Gamma rays were undeflected by a magnetic field. As we talked about at the very beginning of the course, gamma rays are just very, very short wavelength electromagnetic waves. In fact, to differentiate between X-rays and gamma rays, the only difference between the two are the sources. X-rays are electrons that are, X-rays come from electrons that are, usually in the inner shell of atoms, but basically just about anything that's non-nuclear in fashion that generates electromagnetic waves in this realm is typically called an X-ray. For instance, when we produce Bremsstrahlung radiation, which is an electron slowing down as it approaches a metal ion, this is called X-rays. Gamma rays are any electromagnetic radiation that is coming from the nucleus. So that is the main difference there. So again, different types of radioactivity that The most common three types are alpha, beta, and gamma. Again, our alpha particles were identified to be, in fact, helium nuclei, 2 protons, 2 neutrons. Beta particles are electrons, or their antimatter counterpart, which is the positron. And basically, whereas the alpha particles are these big, large particles, and thus their penetration power is not all that great, the beta particles, being much smaller and only interacting through the electromagnetic force, will go much deeper into the material that they are irradiated onto. Gamma rays are the most penetrating because, of course, they're very short wavelength electromagnetic waves. And by the way, with gamma rays, the more energetic the gamma ray, actually, the more penetrating it is. We will talk about that when we get to gamma rays, that shorter wavelength gamma rays can be more dangerous because they're harder to shield for, whereas less energetic gamma rays are easier to shield for, but are more likely to deposit their radiation. Let's start with alpha decay. Alpha decay, as we talked about, is the emission of alpha particles. So it's almost like these nuclei give off a little mini nucleus. And really, most of the place where we see alpha decay, and you can see the alpha decay in yellow on this isotope chart, we have our neutrons on the vertical, we have the protons on the horizontal. And we note that, right above right above a neutron number of 82, we start getting the emission of these gamma rays. And above element 82, which is lead, it really, really becomes very common. Now, in terms of alpha decay, there's really not a lot of it that takes place, at lower masses. There are a few clumps down here of alpha decay, which occur due to interesting resonance phenomena. But again, alpha decay is primarily a very heavy nucleus trying to get rid of some of its mass. More specifically, what it's trying to do is it's trying to reduce its atomic number, because what makes the nucleus less stable, which actually reduces the binding energy, is the presence of the Coulomb force. So if we can shed some protons, and obviously the alpha particles are half protons, half neutrons, if we can shed some of these protons, we can reduce this electrostatic repulsion. And that makes the binding energy greater, because the strong force is very, very short in terms of its influence, meaning that as these nuclei grow larger and larger, the strong force holds onto them, each nucleon, with less and less force. So again, alpha particles, we have a parent isotope. What happens is, the nucleus can become unstable. I guess this is a little oversimplification. Typically, what happens is, inside the parent isotope, we tend to get these alpha particles that actually condense. Again, this is an overly simplistic model, because what's happening inside the nucleus is very, very complicated. But these alpha particles can actually condense, and then they will penetrate through this energy barrier and leave the nucleus. But because they're doing this quantum tunneling, which is completely determined by probability, there is an associated half-life of these alpha emitters, which is really related to how much tunneling that the alpha particle has to do. The alpha particle only has to do a little bit of tunneling through this barrier, then you're going to have a short half-life, because it's going to be easier for the particle to make it through. If the energy barrier is much, much more substantial, then the half-life is going to be obviously much longer. So one question I always had as a student, taking modern physics or nuclear physics was, why an alpha particle? Okay, if you're trying to get rid of protons, why not just get rid of protons? Well, it's pretty complicated, but it's also associated with binding energy. Now, again, if we think about a proton or a neutron, when it's free, there is no nuclear potential energy here. Okay, they're free. So in order to get a proton out of this well or a neutron out of this well, okay, they're going to have to be quite energetic. And, therefore, it's going to be much more difficult for them to leave. But if we're forming these helium nuclei within it, and again, I can't pretend to be able to simplify this to something that is easy to picture in our minds, but we can sort of think of the helium nuclei as coming together before the emission. The binding energy is reducing the overall energy of the particles, and the helium nuclei again has a much higher binding energy. Binding energy again is negative energy. So when we think about binding energy, we should think about it in terms of an energy loss. So forming these condensate, condensed particles within the nucleus allows them to be emitted. There's actually something, we'll talk about this in a little bit, and this is sort of a more advanced idea. There's something called a Hoyle state for carbon-12, where it actually, when we get to alpha, triple alpha fusion, there's actually a Hoyle state where the nucleus itself behaves as if it's three bound helium-4 nuclei. And this sort of confirms the idea that particles within the nucleus can actually group up into smaller units like an alpha particle. So in any case, what happens here is the alpha particle is going to have to make it through this energy barrier. Now, if it were just a classical particle, that helium would stay in there. That alpha particle would stay in there, would never be able to leave, because with its energy, okay, that energy, that potential energy barrier that it has. And again, here is what the potential well looks like for the strong force. Again, very much simplified here. And then we know that for the Coulomb force, the potential energy goes by 1/r. So the electromagnetic force produces this potential barrier up to this point where the strong force kicks in. And what this alpha particle has to do is penetrate through there. And as it does so, or I should say, as the barrier gets thicker and thicker, the probability becomes less and less that it's going to be able to make it through. So again, alpha particles, alpha emissions, these alpha particles undergo quantum tunneling to make their way out of this nucleus. In terms of the reaction, if we write the reaction, we would write it as X, element X is the parent with some atomic number Z, atomic mass number A, that because we're giving off a helium nuclei, we would reduce the atomic mass number by 4, reduce the atomic number by 2. And again, the helium nucleus is what breaks free, or the alpha particle is what breaks free. So for instance, the most common isotope of uranium is uranium-238. This has an atomic number of 92. It has an atomic mass number of 238. And in order to find out what it would decay into via alpha decay, we take the atomic mass number and reduce that by 4, take the atomic number reduced by 2, and you look on the periodic table of elements and you go, 2 over, and we get, element 90 is thorium. So uranium-238 via alpha decay becomes thorium-234, and it releases helium. Now, this brings up a really important point about alpha decay and geology. Inside the Earth, there is, quite a bit of uranium and thorium that decays into helium, and of course, helium is inert, so it tends not to, it doesn't, chemically bond with any of the minerals, so it is going to build up and slowly try to make its way to the surface. And what's interesting is that the generation of natural gas sort of works the same way. When organic matter breaks down deep within the earth, it generates crude oil and it generates natural gas. Natural gas is the volatile form, and natural gas is going to try to make its way to the surface. So the decay of organic matter and the radioactive decay are both going to produce gases which are going to follow fractures upward. Sometimes they're trapped by salt domes, and our primary source of helium, because helium is inert, it's going to just try to escape from our atmosphere due to its low atomic mass. Our primary source of helium is actually from natural gas wells. And helium, again, is very, very important in terms of its industrial applications. We use it to cool objects to very, very cold temperatures. For instance, superconducting magnets in MRIs. 23% of the usage of helium in industry is for cryogenics. Electronics for manufacturing chips. Helium is very, very important to create an inert atmosphere. Also for the generation of fiber optics. Welding, there's other noble gases that we do use for welding, but helium is important there. Leak detection. Helium is a very, very small atom, and we use mass spectrometer leak detectors to try to find out when we have a leak in some type of vacuum system. It's used for diving, deep sea diving. If you breathe in nitrogen, you will actually increase your chance of getting the bends. So deep sea divers, instead of mixing oxygen with nitrogen, which is the normal composition of our air, will mix in helium with oxygen instead. You don't want pure oxygen because that creates its own problems at high pressures of deep diving. So they'll mix the helium in with oxygen. So again, helium, a very, very important element in terms of industry. In World War II, the United States, which is one of the largest producers of helium, would not export helium to Nazi Germany, before World War II. And of course, this led to, in part, there were other reasons too, but this led in part to the Germans using hydrogen in their dirigibles. And of course, the Hindenburg ended up, hydrogen is a more buoyant gas, so that's an advantage there. But we know that hydrogen is also flammable. That led to the Hindenburg, of course, exploding at Lakehurst in New Jersey. Again, helium, very, very important, but all helium that we obtain is actually through alpha decay. Alpha decay of primarily thorium and uranium inside the Earth. And again, this helium is going to try to make its way to the surface, and we can tap a lot of this in the Permian Basin. This is why the United States is such a big producer of helium, because the Permian Basin, some of these wells have a very, very high percentage of helium with the natural gas that comes out. So these very productive wells, which again, the Permian Basin is very important for the production of crude oil, for natural gas, but also for helium. And you can see here that uranium and thorium will actually decay via alpha decay and also beta decay. We'll get to that in a little bit later. But as uranium and thorium decay and eventually settle down to lead, they generate a large amount of helium in the process. Here is one of the decay series. This is the uranium series. And what we see here is we start out with uranium-238. That'll decay into thorium-234, does two betas to become uranium-234. But again, here's an alpha to thorium, an alpha to radium, an alpha to radon, an alpha to polonium, an alpha to an unstable isotope of lead, lead-214. You can do two betas again, decay to lead again, decay to radioactive mercury, but eventually it finds its way through a number of different routes to lead-206. And every one of these reactions here, okay, every one of these reactions is going to release helium in the process. If we start with thorium instead, we start with thorium-232. Again, you can see quite a few alpha decays before we finally settle on lead-208. And there's one more, there's actually two more series. I'm just going to show the Neptunian series I don't show, but the actinium series goes from uranium-235, less common isotope than uranium-238, but it was more common when the Earth was much younger. But again, that results in another isotope, lead-207. Again, many, many emissions of helium in the process. So when you go to the store and you get that helium balloon, you are actually getting a balloon full of radioactive decay material. It's not radioactive. Don't worry about that. But the helium itself was a result of these nuclei giving off these radioactive particles of radiation. I got to be careful there. In geology, these different chains that we showed before, the uranium chain, the thorium chain, the actinium chain, the Neptunian chain, allow us to actually determine the age of some rocks. Again, uranium-238 through many different decays will eventually become lead-206. Okay, the longest half-life in there is about 4.5 billion years, about the age of the Earth. Uranium-235 will decay into lead-207. All right, that takes a shorter time. That takes 0.7 billion years, on average. And then finally, thorium-232 has the longest half-life, and this decays into lead-208. So what typically happens is there is a mineral known as zircon, which is zirconium silicate. And this will oftentimes incorporate impurities of uranium and thorium into its crystal lattice. And it will not incorporate lead. So when these crystals form, here's a very beautiful zircon crystal. But typically we're looking at these microscopic crystals. When they form, it's basically a clock that's starting to tick. The uranium-238, the uranium-235, the thorium-232, as time goes by, okay, there's no lead in the crystal when it first forms, will begin to be converted into this lead. And if we measure the ratio between how much of the original isotope we have compared to how much of this daughter isotope, we can determine the age of the rock. So this has been very, very important when you wonder, talk about the Laurentian Shield up in Canada. How do we know that that's one of the oldest rock formations in the world? We know this because the zircon crystals give us a very exact date as to when that was formed, within a few million years. In terms of hazards to us, this is radioactive material. It does produce ionizing radiation. Alpha particles are leaving their nuclei with a lot of energy, enough to break atomic bonds. And generally, alpha particles are not an external hazard to us, meaning that if you're holding a rock that is emitting alpha particles, you don't really have to worry about these alpha particles because they're not going to penetrate the dead tissue of your skin. They barely penetrate a piece of paper. The problem is if you somehow get this material into your body, then these alpha particles, which are very, very large, have a lot of energy to them, typically about 7 mega electron volts. They're going to do a lot of damage. They're going to do a multiple ionization when they enter the body. So one example where this was done nefariously was the 2006 poisoning of Alexander Litvinenko. And this was done by the Russians, probably at Putin's orders. And he was a former KGB agent who had defected to the West, and he was a big critic of Putin. And somehow it's thought that they introduced the polonium-210 into his tea. He became poisoned, and you can see what he looked like prior to the poisoning, and obviously as he was dying of radiation poisoning. And he was very public about his poisoning. He, acknowledged the fact that, he was given a fatal dose and there's nothing that they could do. So he wanted to show the world exactly what had happened. And this picture was taken soon before he died. Once you ingest this stuff, it's very difficult to rid the body of it. And with the alpha particles, they do a lot of damage before you even know what's going on. The other issue that we have is natural alpha hazards, because radon gas is a large alpha emitter. In fact, radon will actually decay into solid radioactive elements. Again, if we go back to our chain right here, let's go back to the more common forms of radon. Here's radon-222. Radon-222 will decay into polonium-218. And if you have a lot of radon in your house, you inhale the radon, okay? If it decays to polonium, polonium is a solid. So it will adhere to the sides of your lungs and emit these alpha particles, which typically wouldn't be a problem for you because your skin would protect you, but now it's inside the living tissue of your lungs, and the polonium decays into lead, which is also solid, which decays into bismuth, tellurium, mercury. All of these stay within the lungs until they finally decay to lead-206. And lead, lead's toxic, but it's not the toxicity of lead that's such a problem. It is the alpha particles that are emitted as it decays to lead, which can cause lung cancer. Here is, again, radon decaying into polonium in the thorium series, so we have the same problem there. And the actinium series, which is the less common example, again, polonium, lead, bismuth, down to lead eventually. So again, not an internal hazard. We'll talk about, I'm sorry, not an external hazard, but we'll talk about alpha particles as an internal hazard later on. One good application of alpha particles and alpha emitters is the smoke detector, and smoke detectors save a large number of people every year throughout the world by getting people out of burning buildings quickly and maybe addressing a fire which is not uncontrollable before it gets out of control. In any case, smoke detectors work by a very simple principle. A alpha emitter like americium, okay, americium is a radioactive waste product. So otherwise we'd be burying this in so actually we don't bury things in the soil. We actually keep them in cooling ponds because we haven't found a way to dispose of radioactive waste yet. But we haven't come up with a politically viable solution in this country. But in any case, americium, as it decays, gives off alpha particles, and these alpha particles ionize the air. And these ions can carry electricity. So as long as the americium is giving off alpha particles, you have ions between these two electrodes, and a small current will run between the two electrodes, indicating that the air is clear. If I introduce smoke into the smoke detector, the smoke particles will adhere to the ions, or the ions will stick to the smoke particles. And I no longer have a weak plasma here. I now have nothing but neutral air. No electricity will flow anymore, or the electrical current will become less, and that'll set off an alarm, telling you that you have these aerosol particles present, and hopefully it's not due to a fire. Hopefully it's just left something in the oven too long and it's giving off smoke, or I don't know, the fireplace flue wasn't closed. But in any case, this is a very important application of an alpha emitter, and it's not dangerous. These smoke detectors, yes, they give off a little bit of radiation, but you get so much more from the earth naturally that the amount of radiation from these things are negligible. Not to worry. Okay, so those are alpha emitters. Again, if we think about alpha emitters are taking a very heavy nucleus, typically where the large number of protons is causing a significant repulsive force, and this wants the nucleus to actually get lighter. When we looked at the binding energy, we saw that around iron or nickel, that's where we have the highest binding energy. So those represent the most stable nuclei. We can also get instability in nuclei if we have too many protons or too many neutrons. All right. Thinking about the shell model, we fill up different levels of the nucleus, just like we fill up different levels of the atom. Okay. If you think back to chemistry, we fill up the 1s shell first, then you go to the 2s and the 2p. All these electronic levels, you just keep filling up in the simple model of the electron in the atom. Very similar in the nucleus. However, it's more complicated because the electronic states are more or less determined by the charge of the nucleus. Here, the levels of the nucleus are determined by the interaction between the nucleons themselves. So it's a very, very complicated interaction. But in any case, with regard to the levels, you keep filling them up, and the heavier nuclei are more neutron rich because the Coulomb repulsion will push up the proton levels a little bit higher, giving them more energy. But you basically want to have the most energetic proton being similar in energy to the most energetic neutron. So if I have too many protons, I will have the proton energies unusually high and the neutron energies much lower than that. Systems like to go to their lowest energy state. So if I could replace the protons with neutrons, that would make that nucleus more stable. Conversely, if I have too many neutrons compared to protons, the nucleus is going to want to, even out that. So the weak force, again, it can produce a push and a pull force, but that's not so important here. The weak force can actually mediate an interaction where a proton can be turned into a neutron can be turned into a proton. And this is done through what are called W bosons. They're W and Z bosons. But basically what happens here is that the proton is converted to a neutron or a neutron decays into a proton. By either emitting one of these particles or absorbing one of these particles, it's a little bit complicated because we can view these types of interactions as being the superposition of many interactions. But if we want to keep this model very, very simple, let's say a proton wants to convert into a neutron, it can give off these W bosons, which then quickly decay into a positron and a neutrino, or an electron and an anti-neutrino. Okay, so what is the simplest? Let's keep this on the simplest level. What's the simplest way we should think about the weak force? The weak force allows a proton to become a neutron or a neutron to become a proton to help stabilize the different proton and neutron energy levels. Okay, you don't even have to think about this very high level of abstraction here, where we have these virtual particles popping into existence and decaying. So first of all, the weak force has a very short range. The strong force we saw is on the order of about the size of a nucleus, about 10 to the minus 15 meters. With the strong force, the effective range is around 10 to the minus 18 meters, and that's due to the very massive nature, the large masses of the W and Z bosons. So particles interact via the weak force very, very uncommonly, or not very often. That's the way I should probably term that. It's a difficult interaction to happen because it has such a short range. Okay, now let's introduce a new particle called the neutrino. I talked about the neutrino, in terms of the W particle decays into a positron and a neutrino, or an electron and an antineutrino. Neutrinos were discovered by Niels Bohr in 1930 indirectly, because when he looked at a nuclear reaction, he saw the decay products basically being emitted in different directions. But when we went back and added up the momentum wasn't conserved. Okay, one particle will go one way, one particle will go the other way, and all of a sudden they got momentum out of nowhere. So Bohr proposed that there was a third unseen particle. Basically what they did is they did these in cloud chambers where they can see the trails given off by these charged particles. And the neutrino, because it only interacts via the weak force, left no trail. And as a result, could not be seen by these detectors. And Bohr said, well, we have to conserve momentum. Something's going on here. And he proposed the existence of this neutrino, which means little neutral one. Now, neutrinos are very, very difficult to detect. We think that if there's a particle behind dark matter, it also probably only interacts via the weak force. But neutrinos only interact via the weak force, not through the strong force. So if we want to detect a neutrino, it's got to make a very, very exact hit on a proton or a neutron. It'll transfer its energy to the proton or neutron, which will then transfer that energy to the electrons orbiting, and we'll see that neutrino interaction is a flash of light. But this happens at such a low rate that neutrino detectors usually are massive containers of a fluid, which is going to be used to help detect these things. I think only the electron neutrino actually is easily detected. You need other, like germanium detectors. But in any case, massive pools of, I think usually heavy water, are used to detect these things. And you get a flash, every so often from a neutrino hit. Solar neutrinos are a very important topic in terms of the nuclear reactions that we see in the sun. At first, the number of solar neutrinos that we were detecting from the sun was too low. We now know that neutrinos will actually change between 3 different forms as they propagate through space. And we only saw a third of the neutrinos that we expected because it was turning into the other 2 types that we weren't looking for. In any case, when we do a beta decay, one of the byproducts of the beta decay is going to be a neutrino or an antineutrino. And for any type of reaction, we've got to conserve a few things. We've got to conserve energy, first of all, okay? Energy and, of course, mass is related to energy. That has to be conserved, all right? Charge has to be conserved, all right? Also we need to conserve angular momentum, spin. But the other thing we must conserve is something called lepton number, which means that if we produce a lepton, an electron is a lepton, to conserve the number of leptons we've got to produce an antilepton, which is an antineutrino. If we produce a positron, which is an antilepton, positron is the antimatter particle for the electron, we also produce a lepton, which is a neutrino. So in terms of the different types of reactions we can get, beta minus, which is the emission of an electron, will also result in the emission of a antineutrino. So here's beta minus. Here's a beta minus decay. Our parent isotope is X, all right? By emitting an electron, we increase the charge of the nucleus by 1. So if we have something emitting a beta particle, a beta minus particle, it will go up 1 in atomic number. Now that sounds anti-intuitive. You're like, isn't it supposed to be dropping to a lower energy level? If we're adding another proton, isn't that increasing the energy? No, that's not what's happening. One of the neutrons, see, the atomic mass number remains the same. One of the neutrons is converted into a proton that drops the neutron energy level, okay, slightly raises the proton energy level and sort of equalizes that out to the most stable energy configuration. So beta minus decay increases the atomic number. On the flip side, if I turn a proton into a neutron, my atomic number drops by 1. To get rid of that excess charge, I emit a positron. Because I'm creating an antilepton, I also have to give off a neutrino. The last type of interaction that is mediated by the weak force is electron capture. In very massive nuclei, the innermost electron, the electron in that 1s2 shell, or what we call the be the L. What is the L shell? I think it's the L shell. In any case, I'm not remembering my X-ray emissions too well here, but the lowest energy level the innermost electrons orbit so close to the nucleus that an interaction is possible. So what will happen is the nucleus will interact with an electron. Basically, the electron will be absorbed by a proton, converting that proton into a neutron. Because we've gotten rid of a lepton, we have to also balance each side of the equation. Lepton over here, we need to emit a neutrino. So electron capture is interesting because it bridges the world of atomic physics with the electrons orbiting the nucleus with nuclear physics. When the electron is captured, we pull it off the innermost electrons, and this will actually result in the emission of an X-ray also. Now, looking at this chart of radioisotopes, we see that once again, the vertical represents the number of neutrons, the horizontal represents the number of protons. If we are neutron heavy, all these black little boxes here represent stable isotopes. If we are neutron heavy, okay, this blue region right here, we will tend to give off beta minus decay. We'll tend to undergo beta minus decay. And what that means is we will emit an electron to turn this excess neutron, one excess neutron, into a proton. Okay? And get us closer to this midline right here. If we have too many neutrons, which is this side of this chart, we'll do the opposite. We'll undergo beta plus decay. And this is where a proton gives off a positron in order to become a neutron. So you can see this balance happening between the protons and neutrons by either beta minus or beta plus. Too many neutrons, beta minus. Too many protons, a beta plus decay. And again, going back here, the end result, beta plus results in the same outcome as electron capture. All right, with beta plus, we reduce our atomic number. Electron capture, we reduce our atomic number. Just done through different mechanisms. And again, if we give off an electron, we also have to give off an antineutrino. Looking at a smaller level, we can see that for beta minus, okay, the neutron is being converted into a proton. It's giving off an electron and technically an antineutrino. If we want to go to an even higher level of abstraction here, we could view this as actually not just the neutron, but a quark within the neutron emitting a W minus boson. Okay, the W minus boson will decay into an electron and an antineutrino. And as the down quark does this, okay, it converts itself into an up quark. Okay, down quark is a neutron is two down quarks, one up quark. Proton is a down and two ups. So if I convert the down to an up, I've converted my neutron to a proton. Now, I have to warn you here, because this can be viewed, by a number of different interactions. Again, when you're dealing with field theory, we're actually superimposing all the possible reactions that are going to result in the production of an electron and an antineutrino. So this is probably the simplest representation of that, but you could have many more virtual particles participating in this interaction. You've got to consider the superposition of all of them. In any case, carbon-14 decay is a very important phenomena in science, especially for radioactive dating. Carbon-14 is produced by cosmic rays high in the atmosphere. Nitrogen-14 is converted into carbon-14. And basically what happens here is that the carbon-14, as it decays by beta decay. It's not a stable nucleus. Carbon's most stable isotope is carbon-12, okay? 6 protons, 6 neutrons. So carbon-14, 6 protons, 8 neutrons. Obviously, it's real neutron heavy here. So in order to drop down to a more stable energy state, it will emit the beta particle and convert one of those extra neutrons into a proton, become nitrogen-14, and that, of course, is 7 protons, 7 neutrons. Okay, so carbon-14 decays into nitrogen-14, gives off an electron, an antineutrino, and therefore it's more stable. Now, let's go back to the uranium series, because I just used that as an example for alpha decay. All these red arrows represent an alpha decay, and all of those result in the emission of a helium nucleus, alpha particle. But when we look at the uranium series, what happens here is as we give off a proton and a neutron, okay, we're giving off equal numbers of protons and neutrons, we're making the nucleus less stable because, as it's becoming lighter and lighter, the Coulomb force is becoming less, and the proton levels are actually coming down. So to make this more stable, as the proton levels are coming down, we want to make this neutron-heavy nucleus more balanced. And we do this by, of course, undergoing beta minus decay. So uranium-238 decays into thorium-234. That's very neutron-rich for its atomic mass number. So that'll decay, I want to say protactinium, but I can't remember all my all my chemical symbols. But in any case, it beta decays to this isotope here, which then beta decays again to uranium-234. So you can see what happens here. We go from very neutron-rich to less neutron-rich, okay, 4 less neutrons, and then it's going to undergo more alpha decay down to lead-214, and lead-214 is a very rich isotope, neutron-rich isotope of lead. So it needs to get rid of some neutrons. So beta decay, alpha decay, and you can see there are many different paths that it can travel, but eventually it's going to get down to lead-206. So beta decay, this beta minus decay, is also very, very important, as these very heavy isotopes are shedding protons and neutrons. A rebalancing has to take place between the number of protons and neutrons. They become less neutron rich, they're going to give off these beta particles. Again, turning a proton to a neutron in proton-rich isotopes, we emit a positron and a neutrino. This can be viewed as giving off a W plus rather than a W minus. By doing so, the up quark is converted to a down quark. So we have the reverse of what happened before. W plus bosons will decay into a positron and a neutrino. And this can explain how a proton can be converted into a neutron. Okay. By the way, neutrons are not stable particles by themselves. they will naturally decay into neutrons. Protons aren't thought to decay. Well, there's some models that have them decaying, but actually the mass of a neutron is slightly more than the mass of a proton. So outside the nucleus, the proton will not turn into a neutron without the addition of extra energy. So beta plus decay, parent isotope decays into a daughter with one less proton, one more neutron. And a good example of this is oxygen 15, which is used in PET scans. Now, oxygen 15 has a short decay time. So when somebody gets a PET scan, and PET stands for positron emission tomography, okay? They're injected with this short-lived isotope. Oxygen, typically the oxygen, I believe, is in glucose, but it's going to emit a positron. And the interesting thing about these PET scans is that the glucose will go to places where the metabolism is the highest. Oxygen is going to go to places where the metabolism is the highest. So they'll inject people with this radioactive substance that is not harmful to their bodies because it's going to quickly decay, so they're not going to get a large dose. But because cancer cells have a higher metabolism than healthy cells in most cases, okay, they're constantly undergoing cell division. Thus, the uncontrolled cell division means that they're burning through glucose at a much faster rate. We can use this PET scan to actually determine where cancer might be present. So the way it works is this: you inject with the radioactive positron emitters. The positrons themselves are antiparticles. The positrons don't travel very far. They'll quickly combine with another electron. This emits 2 gamma rays, and a special detector will detect each of the gamma rays, and every time it detects 2 gamma rays, it can actually track back to where the gamma ray was emitted. And here's a 3-dimensional image of a person, and unfortunately, this diagnosis does not look, this scan does not look very, very encouraging. Here we see a large amount of emission happening probably around, I'm guessing this is the prostate gland. And not only is the cancer presumably very, very prevalent in the prostate gland, there also seems to be quite a few metastases that have taken place in other organs. This looks like a kidney right here. This looks like a kidney. This looks like the liver, the different lobes of the liver. So this patient, unfortunately, has experienced metastases of the original cancer. The brain normally lights up with the PET scan because our brains actually use a tremendous amount of energy. So again, PET scans are oftentimes used to track the disease and see if it's progressing and if some other therapy, or if the current therapy needs to be changed to something else. Finally, electron capture. Electron capture happens when a proton interacts with a really tight orbiting electron. Now, this doesn't normally happen for lighter elements because we know the Bohr radius is about 10 to the minus 10, 5 times 10 to the minus 11 actually, and the nucleus itself is 10 to the minus 15. But the Bohr radius becomes smaller and smaller. I should say not the Bohr radius, but the radius of the electron waves becomes smaller and smaller and smaller as we go to higher and higher Z elements. So, you go to an element like lead, which has a very, very high atomic number. That's going to have its innermost electrons orbiting very close to the nucleus, and thus there's going to be a stronger interaction. So again, a inner shell electron interacts with a proton, and via the weak force, this can cause a conversion. So for instance, we can imagine here the electron emitting a W minus particle and a neutrino at the same time, converting the up quark into a down quark. Or we could view this as another interaction. The up quark emitting a W plus and converting the electron into a neutrino and converting itself into a down quark. And again, there are actually many, many different interactions. These are the simplest interactions that can result in electron capture. One example of electron capture is nickel 59. This is an isotope that will decay via electron capture 99% of the time. I think the other percent, it'll do a positron emission. But again, the nickel 59 absorbs the electron. The electron combines with a proton. This changes the proton into a neutron. So this becomes cobalt 59, and a neutrino is given off. Potassium. Here's a strange isotope, potassium 40, and it's very, very important for dating rocks. We use the example of zircon, which incorporates uranium and thorium into it, and how it decays into lead. Zircon crystals aren't found in every rock sample, but potassium is a very, very common element in things like feldspar, in different types of mica, in different types of clays. Very, very common element. So the radioisotope potassium 40, which is found in these materials, will decay either into argon 40 via electron capture, or decay into calcium 40 via beta minus. So it either moves up the periodic table or moves down the periodic table. Either Z is increased by 1 through beta minus decay, or the Z is decreased by 1 through electron capture. In any case, 11% of the time it becomes argon. So argon is less favored than the calcium decay. And if we look at the amount of potassium 40 in a sample compared to the amount of argon 40, and remember, argon is a noble gas. It's not going to chemically, react with these materials. As long as that argon can get trapped in the crystal lattice, and we can look at how much daughter isotope we have compared to how much the parent isotope we have, the parent to daughter ratio is going to decrease over time. And this has a half-life of 1.26 times 10 to the 9 billion years. And again, because the Earth is about 4.5 billion years, it's really, really very effective in determining the age of rocks. So there's an interesting example where electron capture is important to is an important tool to geologists for determining the age of rocks. And again, potassium, it's found in most feldspars, mica, clay, and very important tool for radioactive dating. Now, once again, energy levels are quantized. They're quantized within the atom for the electron levels, and of course, they're going to be quantized within the nucleus. When a radioisotope undergoes an alpha decay or a beta decay, it doesn't mean that it decays into the daughter isotope at its lowest energy level. Sometimes the daughter isotope will be left in an excited state, okay? And just like we talked about with the Balmer lines, where it would drop from a higher state to the second state to produce a visible line, or the Lyman lines for electrons would drop from some upper state to the bottom ground state to produce ultraviolet emissions, okay? The nucleus is going to do something very similar. But when nuclear energy levels transition, okay, from a higher state to a lower state, they're not giving off infrared light, visible light, ultraviolet, or even X-rays. They're giving off gamma rays, okay? So again, we talked about quantized atomic states or electronic states giving off infrared, visible, ultraviolet, X-rays, okay? Once we get to the nuclear states, they're giving off gamma rays. And again, it can be an alpha decay, it can be a beta decay, but basically, if the alpha and beta decay don't take you down to that lowest energy level for that daughter isotope, it's going to decay one step further by giving off a gamma ray. So here's an example of cobalt-60. Cobalt-60 will beta decay. Almost always it beta decays, giving off a 0.31 mega electron volt electron, okay? So here's a beta minus decay. It'll decay into nickel-60, but not nickel-60 in its ground state, usually at a state that is 2.5 mega electron volts, MEVs, above the ground state. It will undergo two decay emissions, one from this state to this state, giving off a 1.17 mega electron volt gamma ray, and then another one from this state to this state, 1.33 mega electron volts. So if you have a sample of cobalt, not only is it giving off beta particles, giving off electrons, it's also giving off gamma rays. And this made cobalt a very valuable radioisotope for things such as radiation therapy. I think it was also used for things like X-ray fluorescence. But unfortunately, there have been instances where medical cobalt used for medical devices, has been abandoned or stolen. And unfortunately, people come in contact with this because it's a very strong gamma and beta emitter, can get very, very sick. And here you can see a cobalt-60 gamma spectrum. We see the two peaks, the 1.17 MEV peak, the 1.33 MEV peak. And in spectrometers, one of the problems that you have is you get what are they call these Compton edges, because when the gamma ray hits another atom, it can kick off an electron, and via the Compton effect, produce the shifts in the gamma rays. Here's the decay of americium, and americium is what we talked about in smoke detectors. Americium-241, very strong alpha emitter, and these alpha particles are very energetic, 5.443 mega electron volts, 5.486 mega electron volts. But the americium decays into neptunium. If you look at the periodic table, it goes uranium for Uranus, neptunium for Neptune, plutonium for Pluto. So neptunium is right between plutonium and uranium. The americium decays into an excited level of neptunium, which then give off, fairly, soft as far as gamma rays go. And I say soft because they're lower energy, softer gamma rays, so they're not quite as penetrating as some gamma rays might be. So again, yes, the americium in smoke detectors does give off radiation. Some of this radiation is not contained within the detector itself, but the gamma rays are very, very low level and not very penetrating. Finally, internal conversion. This is an interesting process. And what happens here is, this is sort of similar to electron capture, where the nucleus is in upper energy level, but it couples to one of the inner electrons and just dumps its energy to the electron. And when we're talking about these excited levels, they're in the kill electron volts and mega electron volts. It's more energy than binds that electron, so that electron is just going to go shooting off into space. So it looks like a beta decay, but actually what's really happening is the nucleus has too much energy. It interacts with an electron. The electron is kicked off. Not only is the electron given off, but you also might produce a X-ray as a result, because once that electron is gone, the upper electrons will cascade down and fill that empty shell. So those are the three most common types of decay. All right, there are other types which are much more rare. Actually, we say three. There's alpha. There's two common types of beta, which is beta plus, beta minus. We talked about internal conversion right here, and we talked about electron capture. So these are the most common types of decay that we see. But there are also more exotic types of decay which are possible. These are the ones that we see most commonly. All right.